Let us see the next colligative property, that is depression in freezing point of the solvent in the solution. To understand this property, let us first understand, student, what is the meaning of freezing point. So to understand this freezing point, it is the temperature at which the vapor pressure of the solid equals to the vapor pressure of its liquid. Now to understand what is depression in the freezing point of the solvent, let me take one example. Here I have considered a substance that can exist in two physical states. The first is the solid, and the same substance I am considering in the liquid state. If I see the arrangement of the solid particles, they are in this way, while the liquid will exist in this way. What I want to show here is the strength of the intermolecular interactions. In the solid state, what will happen is the intermolecular interactions which are existing between the first and the second atom, they are very strong, which are weaker in case of liquids, and of course further must be weaker in case of gases. But here I have not considered the gas state. I am considering only solid to liquid, because we are considering solid and liquid. So we are interested only in the vapor pressure, what happens to it. So when I start heating this, what you understand from this is the number of atoms will go in the vapor phase will be less here as compared to this. It will be more here. Why? Because the bonds can be broken easily, and therefore the vapor pressure here must be more as compared to this. So what we conclude here, that the substance, if it exists in the liquid states, its vapor pressure must be more as compared to the substance existing in the solid state. To understand this, what happens to the vapor pressure, student? When I add a solute to any solvent, what happens to vapor pressure? The vapor pressure lowers down or decreases. Now taking that concept of lowering of vapor pressure, let us see the graph what we have seen. To understand this, I am taking a bigger scale graph here. Now this on this y-axis I am taking vapor pressure, and here I am taking temperature. Now let us see what will be the vapor pressure. If you remember the graph for the elevation in boiling point also, the graph was like this. This is for what, student? This is for solvent, right? Now let us see what will happen. The solvent what I am taking is in the liquid state. Now what will be the vapor pressure? Vapor pressure must be high. But as the solvent starts freezing, means what? It is getting converted from liquid to solid. Then what will happen to its vapor pressure? Its vapor pressure will fall. So what will happen to its vapor pressure? Its vapor pressure will fall down. Now this is the liquid state. What will be this state, student? This will be solid. Now what we are interested here is this particular point where the solid is in equilibrium with the liquid, and this particular point the solidification of the liquid starts. Now you might have seen this, when you keep water for refrigerating, what happens? Initially there is a very thin layer of ice which is formed. You can prick that by your fingers. Means what? That is the initiation, or where the ice formation starts, and this is the point. Now if I say this is the vapor pressure, so what will be this point, student? This point will be the, I can call this for the pure solvent, so I will call this as T0. So this is the freezing point of the solvent, so I have taken this as T0. Now what will happen if to the solvent I am adding a solute? There will be lowering of vapor pressure. So where will be the graph, student? It must be below this. So the graph will be in this way. If I see this, where it touches here, and again this is for the solution. When a solute is added, at this point when you see this, where the solidification will take place, again there will be a decrease, right? What is this point is, this point again is the equilibrium solid to liquid. This was for the pure solvent, this is for the solution. Now let us see where the solvent in the solution will get frozen is this. I call this as T. Now what is delta Tf? That is depression in freezing point. If you see the values, this is greater, so it will be T0 minus T, right? So let us see what is the depression in freezing point. All of you have understood, I think, this graph. Now if I take one example, student, if this is for, say for example, 0.1 molar NaCl solution, and this is for the pure solvent, the depression is this much. If I increase this concentration from 0.1 molar to 0.2 molar, keeping the solute same, why I am keeping the solute same, that I will take in the next video, where I will compare the nature of the solute as well as the concentration, and I will be comparing both Kb and Kf. So do watch that video also. So here if I am increasing the concentration, what will happen? There will be further depression in the freezing point. So how the graph will go, students? The graph will be in this way here, and then it will show the depression. So the freezing point will lie somewhere here. So as the concentration will go on increasing, there will be more and more and more depression in the freezing point of the solvent. So let us see what is the meaning of depression in freezing point. So here if I see what is the depression in freezing point, I denote that by delta Tf, and that is equal to your T0 minus T. Now what is this? This is the freezing point of the pure solvent, and what is this T? Is the freezing point of the solvent, but where, student? In the solution. So can I say it is the difference between the two, or the decrease in the freezing point of the solvent in its pure and the solution form? That is delta Tf. Experimentally and thermodynamically, it is proved that depression in freezing point directly depends upon molarity of the solution. Now how I will prove this? That is delta Tf directly depends upon molarity of the solution. What is molarity? It is the number of moles of the solute present per kg of the solvent. So we never keep the equation in this form. So let us remove this. So delta Tf is equal to a constant into molarity. Now this constant, for what we are considering, is for freezing point. So I will just mark this as Kf, right? If the molarity of the solution, if I say that is equal to 1, then what your equation will become, student? Is equal to Kf into 1. Means what? Delta Tf is equal to Kf. Now what is this Kf? This is of course a constant what I have used here, but this constant is called as molar depression constant, or it is also called as cryoscopic constant, right, student? And how you will define this? You can define this, because now this is equal to this, and what is this? This is the decrease in the freezing point when the molarity of the solution is 1. So how I can define this Kf? How I can define this? It is the depression. How I can define this, student? It is the depression in the freezing point of the solvent for a molar solution. Of course, when the Raoult's law is applicable. Now, what is the meaning of a molar? So, you can have one more definition for this. That is, it is the depression in the freezing point of the solvent when 1 mole of the substance is dissolved in 1 kg of the solvent. What I did here, students, I just splitted the meaning of this molar into this format. So both the definitions, they are correct. Now what is the unit of this cryoscopic constant or molar depression constant? For that, I'll take help of this equation. So if I want to find the unit for this molar or cryoscopic constant, what I should do is I should rearrange the equation, and I'll bring this Kf to this side. Now rearrange the equation. It is delta Tf upon m, right? What is this? Is This is the decrease in the temperature. So the unit here will be K. And what is the unit of molarity, students? Is M. So what is the first unit is K molar inverse. Now the second unit will be, or I can have, now it will be K, that is Kelvin, but instead molar, I can say it is mole per kg of the solvent. So what can be the other unit? K. So if I bring this kg up, it will become plus 1. So it will be K kg, and this will become minus 1. So it will be K kg mole inverse. Let us see the derivation and the relation between the cryoscopic constant, depression in freezing point, and the molar mass, because you know that colligative properties, they are used to calculate the molar mass of the solute. So let's see the derivation here. So the derivation, I am continuing that equation, student. So the equation is delta Tf is equal to Kf into M. I'll mark this equation as 1. Now I want to split this molarity. For that you have to make one statement. If W2 kg of the solute with molar mass M2 is dissolved in M1 kg of the solvent, then how you can define molarity? So then molarity of the solution is equal to, so molarity is equal to what, student? Given mass, so it will be W2 upon molar mass into mass of the solvent. If you are not comfortable taking this in kg, what you can do is, in that case you can take this in gram, and in here you multiply the equation by 1000. But as I have taken this in kg, I need not worry about the factor of 1000. I'll put this as equation number 2. Substituting the value of molarity from equation 2 in equation 1, I get delta Tf is equal to, simply substitute the value, student, W2 upon M2 W1. As I said that the colligative properties, they are used to calculate the molar mass of the solute, whereas the molar mass of the solute is M2. So I will simply rearrange the equation. So M2 is equal to Kf W2. This, if I shift here, this will come here. That will be the only change, W1. This is the equation to calculate the molar mass. Now here, what is delta Tf? So you can split that further. M2 is equal to, not required, but required only for the calculations. So it is what, student? This is depression. So it will be T0 minus T, W1. So this is the equations what we will use for the calculations. So this is equation 1 and this is equation 2. Many times the problems, they are asked on this equation also for 2 marks. And if asked on this equation, they are asked for 3 marks. Thank you, students.